Imagine this. You're reading this right now, light bouncing off your screen into your eyes. But what if I told you that in the next 3 seconds, every photon in the universe, every particle of light suddenly froze in place, not just stopped traveling, but ceased to exist in its current form? Your screen would go black, but that's not even the beginning of the nightmare. Because here's what nobody tells you about light stopping. You wouldn't just lose your vision, you would lose your atoms. Your body would begin to disintegrate within microseconds. The sun would explode. The universe itself would start collapsing inward. And the terrifying part? You might have just enough time to feel it happening before your nervous system ceased to function. This isn't science fiction. This is what the fundamental laws of physics tell us would actually occur. The question, what if light stopped, sounds simple, almost childish. But it's actually one of the most profound thought experiments in all of physics, because light isn't just something that helps you see. Light is the fundamental messenger of the universe. It's how atoms hold themselves together. It's how the sun generates energy. It's literally woven into the fabric of space-time itself. When you truly understand what would happen if light stopped, you'll never look at a simple light bulb the same way again. You'll realize that every moment of your existence depends on trillions of photons doing their invisible dance inside your body right now. So buckle up. Over the next 3 hours, I'm going to take you on a journey from basic physics to reality-shattering implications that will fundamentally change how you understand existence itself. We're going to explore what scientists actually know about light, what experiments have revealed about its bizarre properties, and why the scenario of light stopping exposes the most fragile assumptions we make about reality. By the end, you'll understand why this simple question terrifies physicists, and why the answer reveals something profound about the nature of consciousness, time, and existence itself. Before we go any further, do me a favor, hit that subscribe button right now, because this video is going to challenge everything you think you know about reality, and you're going to want to be here for the rest of this journey. Also, drop a comment right now telling me, what country are you watching from, and what time is it where you are? I want to see how many different time zones we have represented as we explore this together. Are you watching this at midnight? Unable to sleep? Your mind hungry for something mind-bending? Or are you on your lunch break, about to have your entire worldview shifted? Let me know. Let's start with what seems like a simple question. What is light, really? You probably learned in school that light is a wave, or maybe a particle. Your teacher probably showed you that prism experiment, where white light splits into a rainbow. They probably told you light travels at 299,792,458 meters per second. But here's the first mind-blowing truth. Nobody actually knows what light fundamentally is. We know what it does. We know how to measure it, manipulate it, use it. But the actual ontological nature of light, what it's made of at the deepest level, remains one of the great mysteries of physics. Let me explain why this matters. In 1905, Albert Einstein published his theory of special relativity, and buried in those equations was a revelation that still hasn't fully penetrated popular consciousness. Einstein showed that light doesn't just travel through space. Light defines what space and time are. The speed of light isn't just a speed limit. It's the conversion factor between space and time. When you move through space, you're actually trading your movement through time for movement through space. Light moves through space at maximum speed, which means it doesn't move through time at all. From a photon's perspective, the moment it's emitted and the moment it's absorbed happen simultaneously. The entire journey, whether it's 1 meter or 1 billion light years, takes exactly 0 time from the photon's frame of reference. Think of it like this. Imagine you're standing on a train platform, and a train zooms by at nearly the speed of light. To you, watching from the platform, the train looks compressed, squeezed thinner in the direction it's traveling. Time on the train appears to move slower. But now imagine you're on the train looking out. To you, the platform appears compressed, and the clocks on the platform seem to be running fast. Both perspectives are equally real. This isn't an illusion or a trick of perception. Space and time are literally different, depending on how fast you're moving. And light, traveling at the maximum possible speed, exists in a frame of reference where all of space is compressed to zero width, and all of time happens at once. Now here's where it gets strange. Light is also an electromagnetic wave, which was discovered by James Clerk Maxwell in 1865. Maxwell unified electricity and magnetism into one elegant set of equations, and when he solved those equations, out popped something unexpected: waves of electric and magnetic fields that could propagate through empty space, and they traveled at exactly the speed of light. This wasn't a coincidence. Light was these electromagnetic waves, but waves need something to wave in, right? Water waves need water. Sound waves need air. So what did light waves need? Scientists in the 1800s invented something called the luminiferous ether, an invisible substance that filled all of space and allowed light waves to propagate. In 1887, two scientists named Albert Michelson and Edward Morley conducted one of the most important experiments in physics history. They tried to detect Earth's motion through this ether by measuring whether light traveled at different speeds in different directions as Earth moved through space. They built an incredibly precise instrument called an interferometer, and they found ... nothing. No matter which direction they measured, light always traveled at the exact same speed. The ether didn't exist. Light didn't need a medium to propagate through. It could travel through pure vacuum, through absolute nothingness. This created a profound crisis in physics. How could waves exist without something to wave in? The answer came from quantum mechanics, which revealed that light has a split personality. It's simultaneously a wave and a particle, a property called wave-particle duality. Light travels as a wave, but interacts as particles called photons. This was demonstrated conclusively in experiments by Max Planck in 1900 and Einstein in 1905, when they explained something called the photoelectric effect, work that earned Einstein his Nobel Prize. Here's what that means in practice. When light travels from a star to your eye, it acts like a wave, spreading out in all directions. But when it hits your retina, it arrives as discrete packets of energy individual photons that trigger individual molecules in your eye cells. Your visual system doesn't detect the wave. It detects individual particle impacts, millions per second. The wave tells you where the photons can go. The particles tell you where they actually went. As physicist Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." But here's the truly bizarre part, and this is where things start getting really weird. According to quantum field theory, developed throughout the 20th century by physicists like Paul Dirac, Richard Feynman, and Julian Schwinger, photons aren't really particles in the traditional sense. They're excitations in an underlying quantum field called the electromagnetic field that permeates all of space. Think of it like ripples on the surface of an infinite ocean. The ocean itself, the electromagnetic field, is always there, filling every cubic centimeter of space. When energy gets pumped into this field, it creates ripples, disturbances, patterns of vibration. Those vibrations are what we call photons. This means that when we ask, "What if light stopped?" we're not really asking, "What if photons stopped moving?" We're asking, "What if the electromagnetic field itself ceased to vibrate?" And that's when things get truly apocalyptic. Because that field isn't just carrying light that you see. It's also responsible for literally holding atoms together. Let's go deeper. You think of your body as solid, right? You feel solid. You can touch a table and it feels solid. But here's a revelation that should blow your mind. You are almost entirely empty space. An atom is about 99.9999999 0.00000000999996% empty space. The nucleus of an atom is like a marble in the center of a football stadium, and the electrons are like gnats flying around the outer walls. So why don't you fall right through your chair? Why does anything feel solid at all? The answer is light. Well, more precisely, the electromagnetic force carried by photons. When your hand touches a table, the electrons in the atoms of your hand and the electrons in the atoms of the table repel each other through electromagnetic force. Photons are constantly being exchanged between these electrons. They're the messenger particles that carry the electromagnetic force. These are virtual photons, quantum fluctuations in the electromagnetic field that pop in and out of existence too quickly to be directly observed, but their effects are very real. This exchange creates what feels like solidity. You're not really touching the table in any conventional sense. The electromagnetic fields generated by the electrons in your hand and the electrons in the table are pushing against each other through the exchange of virtual photons. And that repulsion is what you perceive as the sensation of touch. Now imagine all of that stopping. If the electromagnetic field ceased to vibrate, if photons, both real and virtual, suddenly stopped being exchanged, the electromagnetic force would essentially vanish. Electrons would no longer be held in their orbits around nuclei. The repulsion between electrons that creates the sensation of solidity would disappear. Your atoms would begin to collapse. But wait, you might say, don't atoms stay together because electrons orbit the nucleus like planets orbit the sun? That's what most people learn in school, with those nice diagrams of electrons circling around the nucleus in neat circular paths. But here's the thing, that model is wrong. It's a useful approximation for teaching basic chemistry, but it's not how atoms actually work. In reality, electrons don't orbit at all. They exist in something called probability clouds, regions of space where they have a high probability of being found. These clouds are solutions to the Schrödinger equation, which describes how quantum systems evolve over time. And here's the crucial part. These electron probability clouds, these orbitals, are stable configurations of the electromagnetic field. The electron is constantly interacting with the electromagnetic field, constantly exchanging virtual photons with itself and with the nucleus. This interaction is what creates the stable patterns we call atomic orbitals. If the electromagnetic field stopped working, these patterns would collapse immediately. Think of it like this. Imagine you're watching a beautiful sand mandala being created by Tibetan monks. The intricate patterns are stable as long as someone keeps carefully placing each grain of sand. But the moment they stop maintaining it, the moment wind blows across it or someone walks by, it collapses into random noise. Your atoms are like that mandala, except instead of monks placing sand, it's photons constantly being exchanged at the quantum level that maintain the patterns we call electrons, atoms, molecules, and ultimately, you. But the collapse wouldn't be random, it would be catastrophic. Without the electromagnetic force, electrons would no longer be confined to their orbitals. The probabilistic barriers that keep them in place would vanish. Some electrons might simply escape their atoms entirely, flying off in random directions. Others might collapse into the nucleus. And when an electron collapses into a nucleus, it combines with a proton to form a neutron and releases a neutrino, a process called electron capture. This normally only happens under extreme conditions, like inside collapsing stars. But without the electromagnetic force maintaining atomic structure, it could happen spontaneously. Within microseconds, every atom in your body would begin disintegrating. Your DNA molecules, held together by electromagnetic interactions between atoms, would fall apart. The proteins that make up your cells, your muscles, your bones, all held together by electromagnetic forces, would dissolve. Your neurons, which fire by moving charged ions across electromagnetic barriers, would cease to function. You would lose consciousness almost immediately, probably within a few milliseconds, before your nervous system had time to register what was happening. And your body, losing its structural integrity, would begin to collapse into an amorphous mass of subatomic particles. But you know what's even more terrifying? You wouldn't be alone. This would be happening to everything simultaneously. Every human, every animal, every plant, every microbe on Earth would be disintegrating at the same time. The ground beneath your feet would lose its structural integrity. The air around you, held together as molecules by electromagnetic forces, would break apart into individual atoms, which themselves would begin to collapse. The Earth itself would begin to disintegrate. Now let's talk about the sun, because what happens there is even more spectacular and terrible. The sun is a giant ball of hydrogen plasma, held together by gravity and powered by nuclear fusion in its core. But here's something most people don't realize. The sun is constantly trying to explode. Right now, this very second, the sun is generating enough energy in its core to blow itself apart. So why doesn't it? The answer is a delicate balance between two forces: gravity trying to crush the sun inward, and radiation pressure from all those photons being generated in the core, pushing outward. Inside the sun's core, temperatures reach about 15 million degrees Celsius. At these temperatures, hydrogen atoms are moving so fast that when they collide, they can overcome the electromagnetic repulsion between their positively charged nuclei and fuse together, creating helium and releasing enormous amounts of energy in the form of photons. These photons try to escape, but the sun is so dense that they constantly collide with atoms, getting absorbed and re-emitted billions of times. A single photon generated in the sun's core takes about 100,000 to 200,000 years to random walk its way from the core to the surface, constantly bouncing around. This creates tremendous outward pressure that counterbalances gravity. The sun is in a stable state called hydrostatic equilibrium. Gravity pulls inward with a certain force, and radiation pressure pushes outward with exactly the same force. It's like an incredibly precise standoff that's been maintained for 4.6 billion years. But it's maintained by photons. Take away the photons, take away light, and suddenly there's only gravity. The radiation pressure vanishes instantly. What happens next is called gravitational collapse. The sun, no longer supported by outward radiation pressure, would begin falling inward on itself. The outer layers would fall toward the core at increasing speed, accelerating as they got closer to the center. This is where things get really interesting, because when massive objects collapse under their own gravity, they heat up. The gravitational potential energy is converted into kinetic energy into heat. Here's how fast this would happen. The sun has a radius of about 696,000 kilometers. The gravitational free fall time for a sphere is determined by its density and the strength of gravity. For the sun, calculations show that the collapse would take somewhere between 27 and 30 minutes. In less than half an hour, the entire sun would crush itself down to a fraction of its current size. The outer layers would fall inward at speeds of thousands of kilometers per second. The core would heat up dramatically as all this mass compressed into a smaller volume. And here's the catastrophic kicker. As the sun compressed, the temperature in the core would skyrocket. Within minutes, it could reach temperatures exceeding billions of degrees, far hotter than the sun's current core temperature. At these temperatures, nuclear fusion would suddenly accelerate dramatically. New fusion reactions that don't normally occur would start happening. Helium would fuse into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. The sun would flash burn through millions of years of nuclear evolution in a matter of minutes. But here's the problem. Fusing elements up to iron releases energy, but fusing iron absorbs energy. When the core became iron, the fusion process would suddenly stop being exothermic and become endothermic. It would suck energy out of the core instead of releasing it. The core, suddenly losing its thermal support, would collapse even faster. Within seconds, The core could implode catastrophically, and the infalling outer layers, suddenly meeting a rebounding shock wave from the collapsing core, would be blasted outward in a massive explosion. The sun would essentially undergo a supernova-like explosion. Now, our sun isn't massive enough to go supernova under normal circumstances. It doesn't have enough mass to trigger the runaway collapse needed for a proper core collapse supernova. But if light suddenly stopped and the sun lost its radiation pressure support, the sudden collapse and heating could trigger explosive nuclear burning on a scale never seen in a star of the sun's mass. It wouldn't be a perfect supernova, but it would be catastrophic. The explosion would release an enormous burst of energy. Even without photons to carry this energy away as light, the explosion would generate massive shock waves, plasma, and a flood of neutrinos. But here's the thing, this energy would have nowhere to go. Remember, we're in a universe where photons have stopped existing, where the electromagnetic field has ceased to function. The energy from the explosion couldn't be carried away as electromagnetic radiation. It would be trapped as kinetic energy, as mass physically moving outward at tremendous speed. The sun would blow itself apart, launching billions of tons of plasma outward at a significant fraction of the speed of light. And 8 minutes and 20 seconds later, nothing would happen to Earth, because the explosion, traveling at less than light speed, would still be on its way. We'd have a brief grace period where the sun had already exploded, but we didn't know it yet, because the information about the explosion couldn't reach us faster than the speed of light. But wait, if light stopped, how would we even know the sun exploded? We wouldn't see it. The sky would have already gone dark the instant light stopped. We'd be sitting in darkness, our atoms disintegrating, completely unaware that the sun itself had just destroyed itself. The physical plasma from the explosion would eventually reach us, days or weeks later, depending on exactly how fast it was moving. But by then, Earth itself would already be a very different place. Let's rewind and think about what happens to Earth specifically, because the story there is its own kind of apocalypse. Earth is a complex system with many interacting parts, and almost all of them depend directly or indirectly on light. But let's start with the most immediate physical consequence: temperature. Right now, Earth is in thermal equilibrium with the sun. We receive about 1,361 watts per square meter of solar radiation on average. We absorb some of this light, and we radiate heat back into space as infrared radiation. These two processes balance out, which is why Earth maintains a relatively stable average temperature around 15 degrees Celsius. But infrared radiation is light, it's electromagnetic radiation, just at a longer wavelength than visible light. If the electromagnetic field stopped working, if photons ceased to exist, Earth would suddenly stop being able to radiate heat into space. You might think, wait, that's good, right? We'd stop losing heat, so we'd stay warm. But here's the problem. We'd also stop receiving heat from the sun. And more importantly, we'd stop being able to get rid of the heat we generate ourselves. Heat is the random motion of atoms and molecules. When something is hot, its atoms are vibrating rapidly. The only way to cool something down is to transfer that energy somewhere else. In a vacuum, the only way to transfer heat is through radiation through photons carrying energy away. Take away photons, and heat transfer becomes impossible. This creates a bizarre situation. On one hand, the surface of Earth would begin cooling rapidly because it would stop receiving sunlight. The atmosphere would start to freeze. On the other hand, the interior of Earth, which generates heat through radioactive decay, would have no way to shed that heat. It would start to build up. Earth would become thermally isolated, unable to regulate its temperature. The surface would get cold fast, really fast. Without sunlight, temperatures would drop below freezing within hours. The atmosphere would begin to condense. Oxygen and nitrogen would liquefy and eventually solidify. Within days, the air itself would rain down as liquid nitrogen and oxygen, creating bizarre lakes and glaciers of frozen atmosphere. The oceans would freeze over completely within weeks. Earth would become a frozen ball of ice in space. But beneath the surface, things would be getting hotter. Earth's core is kept hot by radioactive decay uranium, thorium, and potassium atoms breaking down and releasing energy. This generates about 44 terawatts of heat continuously. Normally, this heat slowly conducts through the mantle and radiates away from the surface. But with no way to radiate heat into space, with thermal radiation impossible, the heat would start building up. The mantle would slowly heat up over months and years. Eventually, the crust might crack and fracture from the thermal expansion underneath. But we're getting ahead of ourselves, because there's another immediate consequence of light stopping that we haven't discussed. Chemistry stops working. Think about this. Almost every chemical reaction you know involves electrons. Electrons moving from one atom to another. Electrons sharing between atoms to form bonds. Electrons getting excited to higher energy states and then falling back down. And all of these processes involve interactions with the electromagnetic field. They involve the exchange of photons. Chemistry is fundamentally applied quantum electrodynamics. Take away the electromagnetic field, and chemistry ceases to exist. This has immediate, devastating consequences for life. Your body is a chemical system. Every second, trillions upon trillions of chemical reactions are taking place inside you. Glucose is being broken down to release energy through cellular respiration. Proteins are being synthesized from amino acids. DNA is being transcribed into RNA and translated into proteins. Ions are flowing across cell membranes to propagate nerve signals. All of this is chemistry, and all of it would stop instantly. Your metabolism would simply halt. The ATP molecules that power your cells wouldn't be able to transfer their phosphate groups to other molecules because that's a chemical reaction requiring electromagnetic interactions. The sodium-potassium pumps that maintain electrical gradients across your neurons wouldn't function. Your brain would stop functioning within milliseconds, not because of lack of oxygen, though that would become a problem too, but because the basic chemical processes that allow neurons to fire would cease. But here's something even more profound to consider. If chemistry stops working, then the chemical reactions that create light in the first place would also stop. Even if we somehow restored the electromagnetic field later, even if photons could suddenly exist again, there would be no way to create new ones. No fires would burn, because combustion is a chemical reaction. No light bulbs would glow, because the tungsten filament becoming incandescent is a thermal process that requires atoms to emit photons as they transition between energy states. No LEDs would light up, because they work by recombination of electrons and holes in a semiconductor, which releases photons. The only possible sources of new photons would be nuclear reactions, because those involve the strong and weak nuclear forces, not the electromagnetic force. Nuclear fission and fusion could still theoretically occur. But even then, the neutrons and other particles released in nuclear reactions wouldn't be able to interact normally with atoms, because those interactions also involve electromagnetic forces. The universe would become a dark, dead place where the fundamental processes that power stars, enable chemistry, and allow life to exist had simply switched off. Here's where things get truly metaphysical, and this is the part that keeps physicists up at night. We need to ask a deeper question. Could light actually stop? Is it physically possible for photons to suddenly cease existing? To answer this, we need to understand something called Lorentz invariance and the structure of spacetime. Einstein's theory of special relativity is built on two fundamental postulates. First, the laws of physics are the same in all inertial reference frames. If you're in a spaceship moving at constant velocity, you can't tell whether you're moving or standing still by doing physics experiments inside the ship. Second, The speed of light in vacuum is the same for all observers, regardless of their relative motion. These two principles, combined with basic geometry, lead inevitably to all the weird effects of relativity: time dilation, length contraction, mass energy equivalence, the whole package. But here's the key insight. The constancy of the speed of light isn't just a random fact about photons. It's a fundamental property of space-time itself. Space-time has a structure, a geometry, described mathematically by something called the metric tensor. This structure determines how distances and times are measured, how objects move, how gravity works. And built into this structure is a fundamental speed limit, a maximum speed at which causality can propagate. We call this speed the speed of light. But really, it's the speed of causality, the speed at which information can travel from one place to another. Massless particles must travel at this speed. It's not that they're going really fast and could potentially slow down. They literally cannot exist at any other speed. A photon, being massless, must move at exactly the speed of light in every reference frame. If you tried to slow down a photon, you wouldn't end up with a slow-moving photon. You'd end up with no photon at all. The photon's very existence is tied to its motion at the speed of light. So what would it mean for light to stop? One interpretation: all photons suddenly disappeared, blinked out of existence. But this would violate conservation of energy unless that energy went somewhere else. Energy can be converted from one form to another, but it can't just vanish. So where would the energy that was carried by all those photons go? Let's quantify how much energy we're talking about. Consider just the light in our solar system. The sun emits about 3.8 times 10 to the 26 watts of power. That's 380 trillion watts. Every second, the sun converts about 4 million tons of mass into energy through fusion, and that energy is carried away by photons. At any given moment, there are photons filling the space between the sun and all the planets, carrying this energy outward. If all those photons suddenly vanished, their energy would have to go somewhere. It might convert into kinetic energy of matter, heating everything up instantly. It might convert into gravitational potential energy, warping spacetime. It might create new particles through pair production. But none of these processes would happen cleanly or smoothly. The sudden conversion of such enormous amounts of electromagnetic energy into other forms would be catastrophically violent. Another interpretation: the speed of light suddenly became zero. But this is even more problematic, because the speed of light is a fundamental property of spacetime geometry. Changing the speed of light to zero is equivalent to fundamentally restructuring the geometry of spacetime itself. It would be like saying, what if the angles in a triangle suddenly stopped adding up to 180 degrees? Or what if parallel lines started intersecting? You're not describing a physical event. You're describing the entire mathematical framework of reality changing its rules. And if the structure of spacetime changed such that the speed of light became zero, causality itself would break down. There would be no way for information to propagate from one location to another. Events at different locations couldn't influence each other. The universe would essentially factorize into isolated points, with no way for different regions of space to interact. This isn't just bad, it's logically incoherent. You couldn't have a universe with this property? So here's the mind-bending conclusion. Light can't stop, not just because of physical laws, but because the very concept is logically inconsistent with the structure of spacetime. Asking, what if light stopped, is like asking, what if existence stopped existing? Or what if true became false? It's not that we don't know what would happen. It's that the question itself is asking about something that can't be coherently imagined within any consistent logical framework. And this is crucial: exploring this impossible scenario reveals something profound about the nature of reality. It shows us how deeply light is woven into the fabric of existence itself. Light isn't just a phenomenon that occurs within the universe. Light, or more precisely, the electromagnetic field and the propagation of causality at light speed, is part of the foundational structure that allows the universe to be a universe at all. Let me take you even deeper into the quantum realm, because there's another layer to this that's even more bizarre. We've been talking about photons as if they're little particles flying around, but quantum field theory tells us a very different story. In quantum field theory, reality is made of fields, invisible, omnipresent entities that fill all of space. Every type of particle has a corresponding field. There's an electron field, a quark field, a neutrino field, and yes, an electromagnetic field. These fields are always there, everywhere, even in what we call empty space. The vacuum of space isn't actually empty, it's seething with quantum fluctuations. Virtual particles constantly pop in and out of existence, borrowing energy from the vacuum for infinitesimally short periods of time in accordance with the Heisenberg uncertainty principle. These aren't real particles that you can detect, but their effects are very real. They create measurable forces and can be observed indirectly through phenomena like the Casimir effect and the Lamb shift. The electromagnetic field, even in vacuum, is never truly zero. It fluctuates, creating virtual photons that exist for impossibly brief moments before vanishing. These vacuum fluctuations have energy, quite a lot of it, actually. When you calculate the energy of quantum vacuum fluctuations across all possible wavelengths, you get an answer that's technically infinite, which suggests our theory is incomplete. But even if we introduce reasonable cutoffs to make the calculation sensible, the vacuum energy is enormous. Now, these vacuum fluctuations of the electromagnetic field have real observable consequences. They cause a subtle shift in the energy levels of electrons in atoms called the Lamb shift, first measured by Willis Lamb in 1947. They create an attractive force between two uncharged metal plates placed very close together in vacuum, called the Casimir effect, first measured by Marcus Sparnay in 1958. These aren't hypothetical. They're experimental facts that we can measure with extreme precision. So if light stopped, if the electromagnetic field ceased to function, what would happen to the vacuum fluctuations? Would they just disappear? If so, where would all that vacuum energy go? The answer is baffling, because vacuum energy is already peculiar. It doesn't gravitate the way normal matter does. In fact, it might be related to dark energy, the mysterious stuff that's causing the universe's expansion to accelerate. If the electromagnetic vacuum energy suddenly vanished, or suddenly converted into another form, the effect on spacetime would be dramatic. Einstein's general relativity tells us that energy curves spacetime. That's what gravity is. Vacuum energy contributes to the curvature of spacetime. Suddenly removing or changing the electromagnetic contribution to vacuum energy would create a discontinuity in the curvature of spacetime. In other words, spacetime itself would suddenly warp in unpredictable ways. This might create singularities points, where the curvature becomes infinite and the laws of physics break down. It might create shock waves in the fabric of spacetime itself, propagating outward at the speed of light. Ironically, even in a universe where light had stopped, disturbances in spacetime itself would still propagate at the speed of light, because that's the speed of causality. The geometry of the universe would suddenly shift, and with it, the trajectories of everything in motion would change instantaneously. But here's where it gets really mind-bending. According to quantum field theory, all particles are excitations of their respective fields. An electron isn't a little ball that exists independently. It's a persistent ripple in the electron field. A quark is an excitation of the quark field. And all of these fields interact with each other. The electron field is coupled to the electromagnetic field. When an electron moves through space, it's constantly emitting and absorbing virtual photons, interacting with the electromagnetic field in complex ways. This interaction isn't just important, it's constitutive. The properties of an electron that we measure, like its mass, and its charge are actually products of its interaction with other fields, especially the electromagnetic field. The bare electron, the electron considered in isolation without any field interactions, has properties very different from the electron we actually observe. The electron you can measure in a laboratory is really a dressed electron, an electron surrounded by a cloud of virtual photons and virtual electron-positron pairs, all interacting in complex quantum mechanical ways. This is described by something called renormalization, one of the most mathematically sophisticated parts of quantum field theory. The basic idea is that the properties we measure for particles are effective properties that emerge from the combination of the particle's bare properties plus all of its interactions with quantum fields. These interactions modify the particle's apparent mass, charge, and other properties. If the electromagnetic field suddenly stopped functioning, the renormalization of particle properties would break down. Electrons would suddenly lose the cloud of virtual photons that normally surrounds them. Their effective properties, mass, charge, magnetic moment, would suddenly change. And it's not clear what they would change to, because our theories don't tell us what the bare properties are. We only know how to calculate the renormalized, measured properties that include field interactions. So electrons would suddenly become different particles with different properties. And since your entire body is made of atoms, which are made of electrons and nuclei, you would literally be made of different stuff. The chemical properties of elements would change. Carbon wouldn't be carbon anymore, at least not in the way we understand it. The entire periodic table would be rewritten. And this would happen not gradually, but instantaneously. Let's talk about something that might seem tangential, but is actually crucial. How do we know all of this? How do scientists study light and electromagnetic fields and quantum mechanics well enough to make these kinds of predictions? This matters because I'm asking you to believe some pretty wild claims, and you should be wondering, what's the evidence? The foundation of our understanding comes from centuries of careful experimentation. In 1861, James Clerk Maxwell derived his famous equations that unified electricity, magnetism, and light. These four equations, written in modern vector calculus notation, describe everything about how electromagnetic fields behave. They've been tested billions of times in countless different scenarios, and they've never been wrong. Every electric motor, every radio transmission, every MRI machine, every laser, all of them work because Maxwell's equations are correct. But Maxwell's equations raised a deep question. What are electric and magnetic fields really? Are they just mathematical abstractions? Or do they represent something physically real? In the early 20th century, quantum mechanics provided an answer, but it was an answer that raised even more questions. Quantum mechanics told us that fields are collections of quantum harmonic oscillators, one oscillator for each possible wavelength at each point in space. And the excitations of these oscillators are what we call particles. This idea was worked out in detail during the 1920s and 1930s by Paul Dirac, who developed quantum electrodynamics, QED, the quantum field theory of electromagnetism. QED makes predictions that are staggeringly accurate. For example, it predicts the magnetic moment of the electron, how strongly an electron behaves like a tiny magnet. The predicted value is 2.0023193.0436256, and the measured value is 2.0023193.0436256, plus or minus 0.0000000000000000035. That's agreement to better than 1 part in a trillion. QED is the most precisely tested and confirmed theory in all of science. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga shared the Nobel Prize in 1965 for their work developing the modern form of QED and solving the mathematical problems involved in making precise predictions. Feynman, in particular, developed a visual technique using what are now called Feynman diagrams, pictures that represent the mathematical terms in QED calculations. These diagrams show particles as lines and interactions as vertices where lines meet. A photon exchanged between two electrons would be drawn as a wavy line connecting two electron lines. Using Feynman diagrams and the mathematical machinery of QED, physicists can calculate the probability of any electromagnetic process happening. They can predict what happens when electrons scatter off each other, how likely an atom is to absorb a photon, what happens when an electron and positron annihilate into pure energy. And every single prediction has been confirmed by experiment to ridiculous levels of precision. But here's what's truly remarkable. These calculations involve virtual particles. When two electrons repel each other, we say they exchange a virtual photon. But you can never detect this virtual photon directly. It exists for too brief a time, violating energy conservation temporarily in a way allowed by quantum mechanics. Yet the effects of these virtual photons are measurable and precise. The Lamb shift I mentioned earlier? That's caused by virtual photons and virtual electron-positron pairs briefly appearing and disappearing around the electron in a hydrogen atom, slightly shifting the energy levels. Willis Lamb measured this shift in 1947, and it matched QED predictions perfectly once physicists figured out how to do the calculation correctly. In 1995, a team led by Gerald Gabriels at Harvard University managed to trap a single electron in an electromagnetic trap and measure its magnetic moment to extraordinary precision. They kept the electron isolated, suspended in space by electromagnetic fields for months. They measured how it wobbled in a magnetic field. The result agreed with QED predictions to 1 part in a trillion. Think about what that means. A theory based on virtual particles constantly popping in and out of existence, on fields filling all of space, on probability clouds and wave functions. This bizarre quantum mechanical picture predicts real measurable numbers to 1 part in a trillion. Reality actually works this way. So when I tell you that if light stopped, electrons would lose their stability and atoms would collapse, I'm not speculating. I'm extrapolating from the most rigorously tested theory in all of science. We know how electrons interact with the electromagnetic field. We know what holds atoms together. We've measured it, calculated it, tested it billions of times. Take away that field, and the math tells us, with absolute clarity, what happens. But the experimental confirmation goes beyond just QED. In 1995, physicists at CERN created the first atoms of antimatter specifically, antihydrogen atoms made of an antiproton and a positron. They lasted only for a fraction of a second before annihilating with normal matter, but they existed. And they existed because the positron orbited the antiproton through exactly the same electromagnetic interactions that make electrons orbit protons. The math works both for matter and antimatter. In 2012, Serge Haroche and David Wineland won the Nobel Prize for developing techniques to observe and manipulate individual photons. Haroche's team could trap a single photon in a superconducting cavity and watch how it interacted with individual atoms passing through. They could see, in real time, the wave function of a single photon collapsing as it was measured. They could observe quantum superposition, a photon being in 2 places at once, and watch it collapse into a definite location when measured. This isn't philosophy. This is experimental reality. Wineland's team, meanwhile, trapped individual ions and manipulated them with laser light, with individual photons, to create quantum states of matter that had never existed before. They created quantum computers using trapped ions as qubits, their states controlled by precisely timed photons. These experiments required understanding light and matter interactions at the most fundamental level possible. And here's something that should blow your mind. In 1997, Anton Zeilinger's team in Austria performed an experiment that demonstrated quantum, entanglement between photons separated by large distances. They created pairs of entangled photons, whose quantum states were correlated in ways that couldn't be explained by any classical theory. When they measured the polarization of one photon, the polarization of its partner, miles away, instantly became determined. This wasn't information traveling faster than light. It was the collapse of a shared quantum wave function. Einstein called this spooky action at a distance and thought it proved quantum mechanics was incomplete. But experiments, performed over and over with increasing sophistication, have confirmed that this is how reality actually works. Photons can be entangled across arbitrary distances. In 2015, Thibaut Perronel and colleagues at MIT did something even more remarkable. They made photons interact with each other directly. Normally, photons pass through each other without interacting. Two laser beams cross, and the light just goes straight through. But by passing photons through a special quantum medium made of ultra-cold atoms, they made the photons bind together into molecules, photonic molecules. Two photons went in, and a bound pair came out, moving together as a single entity. They had effectively given light mass, created particles of light that had inertia and momentum in ways individual photons don't. Why am I telling you all this? Because I want you to understand that when scientists talk about light and electromagnetic fields and quantum mechanics, we're not just making stuff up. We're describing reality as revealed through extraordinarily precise experiments. Every strange claim I've made about what would happen if light stopped is backed by decades of experimental evidence showing how light, matter, and fields actually interact. Now let's talk about what happens to your perception, your consciousness, your subjective experience if light stopped. This is where physics meets neuroscience and philosophy, and things get really interesting. Your brain is an electrochemical computer. Information in your brain is encoded in two ways: chemical signals passing between neurons via neurotransmitters, and electrical signals traveling along neurons via action potentials. Both of these depend fundamentally on electromagnetic forces. The sodium and potassium ions that create nerve impulses move across cell membranes through channels that are controlled by electromagnetic forces. The neurotransmitters that carry signals across synapses bind to receptors through electromagnetic interactions. Your thoughts, your memories, your sensations, your sense of self, all of it is patterns of electromagnetic activity in your brain. If light stopped, if the electromagnetic force ceased to function, your brain would stop working immediately. But here's the question that haunts philosophers and neuroscientists. Would you experience anything in that final moment? Would there be a last conscious thought, a final flicker of awareness before your neurons went dark? The answer depends on something we don't fully understand: the relationship between consciousness and physical processes. There are roughly three schools of thought. First, physicalism. Consciousness is nothing but patterns of physical activity in the brain. If the physical activity stops, consciousness stops instantly and automatically. There's no separate mind that could persist even for a moment after the brain stops functioning. Second, dualism. Consciousness is something separate from physical processes, some kind of non-physical mind or soul that interacts with the brain but isn't identical to it. If this is true, then maybe consciousness could persist for some brief moment after electromagnetic processes stopped, like a record player needle bouncing after the record stops spinning. But this view has serious problems, both philosophical and scientific. Third, panpsychism. Consciousness is a fundamental feature of reality, present at some level in all matter, and what we call consciousness is just a particularly organized form of this ubiquitous awareness. If this is true, then stopping electromagnetic processes wouldn't stop consciousness. It would just radically reorganize it in ways we can't imagine. Most neuroscientists are physicalists. They believe that consciousness is what information processing in the brain feels like from the inside, and information processing requires time. Neurons fire, Signals propagate. Patterns emerge over milliseconds and seconds. Consciousness is these patterns. So if electromagnetic forces stopped and neurons ceased to fire, the patterns would stop and consciousness would cease. But there's a subtle question here about timing. Your neurons don't fire all at once. Consciousness emerges from waves of activity spreading through different brain regions over time. At any given instant, some neurons are firing while others are quiet. When you perceive something, like seeing a red apple, that perception isn't instantaneous. It takes about 100 to 200 milliseconds for visual information to travel from your eyes, through your visual cortex, through various processing stages, and into your conscious awareness. You're always perceiving the past, living in a slightly delayed version of reality, because neural processing takes time. So if light stopped at precisely this moment, there would be neural activity still in progress, patterns still unfolding. For a few milliseconds, perhaps tens of milliseconds, your brain would still be processing information from before light stopped. You might have one last thought, one last moment of awareness, as the final signals propagated through your dying neurons. It would be like a movie projector running out of film, a few last frames flickering by before everything goes dark. What would that last thought be? Would you realize something was wrong? Would you experience the disintegration of your own consciousness? Probably not. The processes that create self-awareness, that allow you to think about your own thinking, are among the most complex and time-consuming in the brain. They require multiple regions communicating with each other over hundreds of milliseconds. If neural activity stopped abruptly, you probably wouldn't have time to become aware that anything was wrong. Your last conscious experience would be whatever you were thinking about in that moment, completely normal, mundane, unaware of the apocalypse unfolding at the atomic level. But here's something even more unsettling. Would anyone be able to tell the difference between consciousness actually stopping versus just all the physical behaviors associated with consciousness stopping? This is a version of the famous hard problem of consciousness, identified by philosopher David Chalmers. We can explain, in principle, all the functional behaviors of conscious beings, how they respond to stimuli, how they report their internal states, how they make decisions. But we can't explain, even in principle, why all of this information processing feels like something. Why isn't the brain just an unconscious biological computer? Why is there subjective experience at all? If consciousness is truly subjective, truly private, then from an outside perspective, there's no way to know whether it persists or not when the physical processes stop. All we can observe is the behavior stopping. The lights go out, metaphorically and literally. But whether there's anyone home experiencing the darkness, that's unknowable from the outside. This leads to a disturbing thought experiment. In our scenario where light stops, every conscious being in the universe would lose consciousness within milliseconds. But from each being's perspective, they just stop. No pain, no awareness, just instant cessation. Like being under general anesthesia. One moment, you're counting backward from 100. The next moment, you're waking up hours later with no memory of the time in between. Except in this case, there'd be no waking up. From the perspective of the universe, nothing would be there to observe what happened next. The collapse of atoms, the disintegration of matter, the explosive death of the sun, all of it would unfold in a universe devoid of observers. And here's where quantum mechanics adds another layer of weirdness. Some interpretations of quantum mechanics, particularly the von Neumann-Wigner interpretation, suggest that consciousness plays a role in collapsing quantum wave functions, in making the merely probable become actual. If all consciousness ceased, what would happen to quantum mechanics itself? Most physicists reject this idea. They think quantum wave functions collapse through interaction with the environment, not through conscious observation. But a few, like Nobel laureate Eugene Wigner, took seriously the possibility that consciousness is fundamental to quantum mechanics. If they're right, then a universe without consciousness might not even be able to maintain quantum coherence. Reality itself might become indeterminate, undefined, a blur of superposed possibilities with no observations to collapse them into definite outcomes. Let me take you to the cosmological scale, because what happens to light stopping affects not just Earth, not just the solar system, but the entire observable universe. And the consequences are so vast, so incomprehensible, that we need to think in entirely different terms. The universe is big, really big. The observable universe has a radius of about 46.5 billion light years, even though it's only 13.8 billion years old. This is because the universe is expanding. Space itself is stretching, carrying galaxies away from each other. And we know the universe is expanding because we observe the redshift of light from distant galaxies. Here's how that works. When a galaxy is moving away from us, the light waves it emits get stretched as they travel through expanding space. This stretching shifts the wavelength toward the red end of the spectrum, longer wavelengths. By measuring how much light is redshifted, we can calculate how fast a galaxy is receding. Edwin Hubble discovered this in 1929, and it revolutionized cosmology. The observation that all distant galaxies are redshifted, and the degree of redshift increases with distance, led to the Big Bang theory. But here's the crucial point. We know about distant galaxies only through light. Every photon reaching us from a distant galaxy has traveled for millions or billions of years across expanding space. The Hubble Space Telescope, launched in 1990, has captured images of galaxies so distant that their light has been traveling for over 13 billion years. We're seeing them as they were when the universe was only a few 100 million years old, shortly after the first stars formed. If light stopped, all of that information would stop flowing. The universe beyond our immediate vicinity would become unknowable. We'd be trapped in our local bubble, unable to observe anything beyond a certain radius determined by how far matter could physically travel in the time since light stopped. But more fundamentally, the expansion of the universe itself is driven, in part, by light. In the early universe, immediately after the Big Bang, the universe was filled with incredibly dense, hot plasma. Photons were constantly being absorbed and re-emitted by particles, creating enormous radiation pressure. This radiation pressure contributed significantly to the expansion of the early universe. Even today, photons contribute to the energy density of the universe, though they're much less important than they were in the early universe. If all photons suddenly vanished, the energy density of the universe would drop instantaneously. According to Einstein's field equations of general relativity, the expansion rate of the universe depends on its energy density. Suddenly removing all electromagnetic energy might cause the expansion to slow down or even reverse. Now, the universe is currently accelerating its expansion, driven by something we call dark energy, a mysterious component that makes up about 68% of the universe's energy density. We don't know what dark energy is. It might be vacuum energy. It might be a new field. It might be a sign that our theory of gravity is wrong on cosmological scales. But if electromagnetic energy suddenly vanished, the balance between matter, dark energy, and spatial curvature would shift. The universe's fate might change. Currently, best estimates suggest the universe will expand forever, eventually becoming so diffuse and cold that stars cease to form, black holes evaporate, and even protons decay over unimaginable timescales, a scenario called heat death. But if light stopped and the energy balance changed, the universe might instead reach a maximum size and begin collapsing back on itself, eventually crunching back down into a singularity, a big crunch. But wait, there's a timing issue here. The observable universe is 93 billion light years across. If light stopped, that information couldn't propagate faster than light. So different regions of the universe would learn that light had stopped at different times, separated by billions of years. The stopping of light wouldn't be a universal simultaneous event. It would be a causally propagating change, spreading outward at the speed of light. Unless the stopping of light was somehow built into the structure of space-time itself at a fundamental level. If space-time itself changed its properties such that light speed became zero, then this change might propagate instantaneously throughout all of space-time. But this gets us back to the logical incoherence problem. If light speed is zero, how does any change propagate at all? Alternatively, imagine light stopped everywhere simultaneously in some privileged reference frame. Maybe the reference frame of the cosmic microwave background, the rest frame of the universe's expansion. This would violate special relativity, which says there's no privileged reference frame. But in our scenario, the laws of physics are already being violated, so maybe that's okay. If light stopped simultaneously in the CMB rest frame, then observers in different reference frames moving relative to the CMB would see light stop at different times due to relativity of simultaneity. It would be bizarre and paradoxical. Here's another cosmic consequence. Black holes would be affected in strange ways. A black hole is a region of spacetime where gravity is so strong that not even light can escape. The boundary of a black hole is called the event horizon, the point of no return beyond which even photons cannot travel outward. But if photons can't exist or can't move, what happens to the definition of an event horizon? Stephen Hawking proved in 1974 that black holes aren't completely black. They emit thermal radiation through a quantum mechanical process, now called Hawking radiation. Virtual particle pairs form near the event horizon. Normally, both particles would annihilate, but sometimes one falls into the black hole while the other escapes. The escaping particle becomes real radiation, carrying energy away from the black hole. Over enormous timescales, this causes black holes to slowly evaporate. But Hawking radiation involves photons and other particles being emitted from near the event horizon. If photons couldn't exist, black holes couldn't evaporate. They'd become truly eternal, truly black. No information could ever escape them. No energy could radiate away. Every black hole in the universe would suddenly stop its slow process of evaporation and become permanently frozen in time. Moreover, the process of falling into a black hole would change. When something falls toward a black hole, from the outside perspective, it appears to slow down and redshift, its light getting dimmer and redder as it approaches the event horizon. It never quite seems to reach the horizon. It just fades away. But if light stopped, this entire visual process would cease. Nothing could be observed falling into black holes anymore. They'd become completely undetectable, except through their gravitational effects. Let's bring this back to something you can relate to personally, because I want you to feel the weight of what we're discussing. Every single thing you've ever seen, every person you've loved, every beautiful sunset, every star in the night sky, every screen you've stared at, all of it reached you through light. Your visual cortex, the part of your brain that processes sight, makes up about 30% of your cerebral cortex. Nearly a third of your brain is dedicated to processing light. Human beings are profoundly visual creatures. About 80% of the information we take in from our environment comes through our eyes. When you remember something, if you visualize it, you're using the same neural pathways that process actual vision. When you imagine the future, when you plan, when you dream literal dreams while sleeping, you're using visual processing. Light isn't just something you see with. It's fundamentally intertwined with how you think, how you remember, how you imagine. If light stopped, you wouldn't just lose your eyesight. You'd lose access to the primary way your brain makes sense of reality. And this would happen so fast that you wouldn't have time to adjust. Blind people who lose their sight gradually can adapt their brains, rewire to emphasize other senses. Hearing and touch become richer. But if sight disappeared instantly, if your visual cortex suddenly had no input and no future prospect of input, what would happen to that third of your brain? In the brief moments before your consciousness ceased entirely, as your neurons fired their last electrochemical signals, would your visual cortex generate hallucinations? When people are placed in complete darkness for extended periods, they often experience visual hallucinations as their visual cortex, deprived of input, starts generating its own patterns. Prisoners in solitary confinement report seeing lights, shapes, even complex scenes that aren't there. Would your dying brain, in its final milliseconds, create a last burst of phantom images? Would you see light even as light was ceasing to exist? Or would there just be darkness? Not the darkness you experience when you close your eyes. That's still a visual experience, the sensation of seeing black. I'm talking about the absence of visual experience entirely, the kind of darkness that exists behind your head, in the direction you can't see because you don't have eyes there. It's not black, it's nothing. Would that be your final experience? But let's zoom out from this moment and think about the bigger picture of what light means to human experience and human civilization. Every civilization on Earth has worshipped light in some form. The Egyptians worshipped Ra, the sun god. Christians speak of Christ as the light of the world. The Hindu festival of Diwali celebrates light's victory over darkness. The Buddha is often depicted with a radiant aura. Enlightenment, in virtually every spiritual tradition, is metaphorically described as light illuminating darkness. This isn't coincidence. Light is our metaphor for knowledge, understanding, goodness, divinity, life itself. Darkness is our metaphor for ignorance, confusion, evil, death. Every language on Earth has idioms connecting light with positive things and darkness with negative things. We see the light when we understand. We're in the dark when we're ignorant. Ideas dawn on us like sunlight. Truth comes to light. This is so fundamental to human cognition that it's hard to imagine thinking without these metaphors. And this makes sense, because for all of human evolution, our survival has depended on light. We evolved under the sun. Our circadian rhythms, our sleep-wake cycles, are governed by light exposure. When light hits the retina, it triggers signals that suppress melatonin production, keeping us awake. Darkness triggers melatonin release, making us sleepy. This is true for almost all animals. Life on Earth has evolved in the presence of a day-night cycle for billions of years. Plants use light to perform photosynthesis, converting light energy into chemical energy and releasing oxygen as a byproduct. This process, worked out in detail by Melvin Calvin in the 1950s, for which he won the Nobel Prize, is the foundation of nearly all food chains on Earth. Herbivores eat plants, carnivores eat herbivores, and at the bottom of it all is photosynthesis converting sunlight into stored chemical energy. Without light, photosynthesis stops, and the entire food web collapses. But even before the collapse of the food web, even before the freezing of the atmosphere, even before the disintegration of atoms, humanity would lose something fundamental to its identity. We are the species that captured fire, that extended the day into night with artificial light, that invented telescopes to gather faint light from distant stars, that built cameras to capture moments of light on film, that created cinema and television and computer screens, all technologies for generating and controlling light. We are, in a very real sense, the species of light. If light stopped, it wouldn't just be the end of seeing. It would be the end of the human project as we understand it. Every photograph ever taken, every painting ever painted, every film ever made, all of them are frozen patterns of light and color, meaningless without light to reveal them. The Mona Lisa would cease to be visible. The Hubble Deep Field image, showing thousands of galaxies in a tiny patch of sky, would go dark. Every sunset you've photographed, every face you've captured on camera, would become inaccessible. And beyond human artifacts, consider natural beauty. The Grand Canyon, whose layers of colored rock tell a story of geological history spanning millions of years, visible only through light and shadow. The aurora borealis, dancing curtains of light in polar skies, created by solar wind particles exciting atmospheric atoms to emit photons, would cease to exist. Rainbows, one of nature's most universal symbols of hope and beauty, are literally refracted and reflected sunlight. They would disappear instantly. Every star in the night sky you've ever wished upon, every planet you've observed through a telescope, every nebula and galaxy photographed by astronomers, all of them would blink out. Not because they physically ceased to exist, but because the photons carrying information about them to your eyes would stop flowing. The universe would become opaque, unknowable, beyond our immediate tactile reach. Now, let's consider the philosophical implications of all this, because we've been dancing around some profound questions about the nature of reality itself. Here's the key insight. Light isn't just a thing in the universe. Light is how we know about the universe. Every scientific fact we know about distant objects comes from light. We know the composition of stars by analyzing their spectra pattern of wavelengths of light they emit. We know how fast galaxies are moving by measuring the Doppler shift of their light. We know the temperature of objects by their thermal radiation, the light they emit due to their heat. This creates an epistemological problem. If light stopped, and we somehow survived, which we wouldn't, but let's imagine, how would we learn anything about the world beyond our immediate vicinity? Touch only tells us about things we're in contact with. Sound requires a medium and doesn't travel far. Smell and taste are even more limited. We'd be reduced to a tiny bubble of direct sensory contact, unable to know anything about the wider world. But it gets deeper. Consider the fact that you're always seeing the past. Light takes time to travel, so everything you see happened in the past. When you look at someone across a room, you're seeing them as they were a few nanoseconds ago, the time it took light to travel from them to your eyes. When you look at the moon, you're seeing it as it was 1.3 seconds ago. When you look at the sun, you're seeing it as it was 8 minutes and 20 seconds ago. When you look at Proxima Centauri, the nearest star, you're seeing it as it was 4.2 years ago. This means you live in a bubble of delayed information. Your immediate now is actually a composite of many different thens, depending on distance. The room around you is nearly simultaneous. The moon is 1.3 seconds in your past. The sun is 8 minutes in your past. Distant galaxies are billions of years in your past. Your subjective present is actually a patchwork of different times, stitched together by your brain into a coherent experience. If light stopped, this entire structure would collapse. Your cone of observability would shrink to exactly where you are right now. Past and present would become meaningless distinctions at any distance beyond your immediate location. You'd exist in a single moment, unable to access any information about anywhere else. But here's where it gets truly bizarre. According to special relativity, simultaneity is relative. Two events that are simultaneous in one reference frame are not simultaneous in another frame, moving relative to the first. This means there's no objective, universal now that spans across space. Different observers in relative motion will disagree about whether distant events happened at the same time or in sequence. Light is what mediates this relativity of simultaneity. The constant speed of light in all reference frames is what forces different observers to disagree about simultaneity. If light stopped, if its speed somehow became zero or infinite, the entire causal structure of time would change. The relationship between cause and effect would break down. Events that were causally connected, where one event could influence another, might become causally disconnected. Events that were causally disconnected might suddenly become connected. This isn't just an abstract philosophical point. The causal structure of space-time determines what's physically possible. It determines which events can influence which other events. It determines the arrow of time, why we remember the past, but not the future, why entropy increases, why causes precede effects. All of this is built on the finite, constant speed of light, Change that, and you're not just changing one property of the universe. You're changing the entire framework within which events occur. Philosopher Hans Reichenbach, in his 1956 book, The Direction of Time, argued that the arrow of time emerges from the causal structure of spacetime, which in turn emerges from the finite speed of light. If light could travel instantaneously, there would be a universal simultaneous present, and the distinction between past, present, and future would collapse. Time would become space-like rather than time-like. The universe would be static, eternal, with no genuine change or becoming. So in a strange way, light is what gives time its flow, its irreversibility, its direction from past to future. Light stopping would be equivalent to time stopping, not in the sense that clocks would freeze, but in the deeper sense that the very distinction between past and future would cease to have meaning. Let me share something that might blow your mind even more. There's a sense in which you are light, not metaphorically, but literally. Your body's atoms are held together by electromagnetic forces, by photons. The warmth of your skin is infrared photons radiating into the environment. When you move, you emit light thermal radiation that can be detected with infrared cameras. In total darkness, you glow, emitting about 100 watts of infrared radiation continuously. But more fundamentally, you're made of atoms. And atoms get their properties from electron configurations, which are determined by electromagnetic interactions. The electron orbitals that determine whether an atom is hydrogen or helium or carbon are solutions to the Schrödinger equation, including electromagnetic forces. The chemical bonds that hold your molecules together are shared electron clouds, stabilized by photon exchange. At the quantum level, you are constantly shimmering with electromagnetic activity, photons being emitted and absorbed, fields fluctuating, electrons hopping between energy states. In a very real sense, your physical existence is maintained moment by moment by the electromagnetic field. You're not a static object, you're a dynamic process, a pattern of energy flows and field interactions that maintains a coherent structure over time. You're like a whirlpool in a river, a stable pattern that persists despite constant flow and change of the underlying substance. If light stopped, that pattern would immediately begin to dissolve. You wouldn't just die. You would cease to be a coherent entity at all. The pattern, that is, you would scatter into disconnected pieces as the field that maintains the pattern stopped functioning. And here's the really profound part. This is true even in normal circumstances. You're constantly dying and being reborn at the atomic level. The atoms in your body are constantly being replaced. You breathe in new atoms, eat new atoms, excrete old atoms. The atoms in your body right now are almost entirely different from the atoms that were in your body 7 years ago. Yet you persist. The pattern persists, maintained by forces and fields, even as the underlying substance changes. This raises deep questions about identity and persistence. What are you, really? Not the atoms, those change. Not the molecules, those turn over on timescales of days to years. You are the pattern itself, the organization, the structure. You are information, encoded in matter, but not reducible to matter. And that pattern is maintained by electromagnetic forces. The Buddhist concept of anatta, non-self, seems remarkably prescient here. You are not a permanent, unchanging self. You are a process, a collection of constantly changing patterns that maintain continuity through time. The electromagnetic field is part of what maintains that continuity. Without it, there is no continuous self at all. We're now about an hour and 20 minutes into this journey, and I want to pause and ask you something directly. How do you feel right now? If you've been paying attention, really digesting these ideas, you should feel a mixture of awe, confusion, maybe some existential vertigo. We've gone from a simple question, what if light stopped, to fundamental questions about the nature of reality, time, identity, and existence. This is intentional. Science at its best doesn't just give you facts. It changes how you see the world. It reveals that the solid, stable, common-sense world of everyday experience is actually a thin veneer over something far stranger and more wonderful. Light seems so simple, so mundane. You flip a switch and lights come on. You walk outside and sunlight warms your face. What could be simpler? But when you dig deeper, when you ask what light actually is and what role it plays in the universe, you discover layers upon layers of complexity and strangeness. You discover that light is the messenger between atoms, the force that holds matter together, the fundamental speed limit of causality, the thing that gives time its arrow and space its structure. You discover that light is woven into every aspect of reality, so thoroughly that asking what would happen if it stopped is like asking what would happen if existence itself stopped. And this reveals something profound about the human project of science and understanding. We live on the surface of an immensely deep reality. We see the tip of the iceberg light as illumination, as something that helps us see. But beneath that surface is an entire hidden world of quantum fields, relativistic spacetime, thermodynamics, and emergent complexity. Science is the process of diving beneath that surface, of exploring the depths. When you learn about science, truly learn it, you're not just accumulating facts. You're training yourself to see deeper, to notice the hidden scaffolding that holds up the apparent simplicity of everyday reality. And once you start seeing that deeper level, you can't unsee it. Light will never be simple again. You'll look at a lamp and think about photons. You'll look at the sun and think about fusion and plasma and radiation pressure. You'll look at your own hand and think about electron orbitals and electromagnetic bonds and the constant shimmer of quantum activity maintaining your existence. This is what makes science beautiful. Not just that it's true, though it is true. Not just that it's useful, though it's immensely useful, but that it expands your consciousness, deepens your appreciation for the astonishing fact that you exist at all in this strange, complex, delicately balanced universe. And here's the empowering part. You now know things that almost no one knew 100 years ago. The quantum mechanics, the particle physics, the relativity, all of this was worked out in the 20th century. Einstein, Bohr, Heisenberg, Schrödinger, Dirac, Feynman, these giants discovered and articulated these truths within living memory. And now you have access to their insights. You're standing on the shoulders of giants, seeing further than any human in history could see until very recently. This should make you feel both humble and empowered. Humble, because you're a tiny pattern of organized matter on a small planet orbiting an ordinary star in an ordinary galaxy among billions of galaxies. Empowered, because you have the capacity to understand, to know, to see through the apparent surfaces to the deeper reality. You are the universe becoming conscious of itself, matter organized in such a way that it can contemplate its own existence. Let's take this in a different direction. I want you to imagine something. What if we could survive light stopping? What if, somehow, we had the technology to maintain atomic structure through some means other than electromagnetic forces? What if we could keep our atoms from collapsing, keep our neurons firing, keep our consciousness intact even without light? What would it be like to live in a universe without light? First, you'd have no vision, obviously, but you'd adapt, presumably, the way blind people adapt. You'd rely more on touch, hearing, perhaps develop technologies that translate other phenomena into tactile or auditory sensations. But there would be fundamental limitations. Without light, there's no way to perceive anything at a distance, except through sound and gravity. Sound requires a medium and doesn't travel through vacuum. Gravity is extremely weak. It would be nearly impossible to detect distant objects through gravity alone. You'd be trapped in a bubble of immediate sensory contact, probably just a few meters in radius. Communication would be limited to sound, vibration, direct physical contact. No wireless communication radio waves are just low-frequency light, part of the electromagnetic spectrum. No fiber optic cables, obviously. No electrical signals through wires, because moving electrons interacts with the electromagnetic field. You'd be reduced to essentially mechanical communication sound waves, physical touch. Computing would be impossible with current technology. All modern computers rely on manipulating electrons, which requires electromagnetic forces. You couldn't have transistors, logic gates, memory storage. You'd have to invent entirely new paradigms of computation based on mechanical systems, perhaps, or nuclear forces, or quantum effects involving the strong or weak force.